In this section, we're going to look at some more advanced probability rules. So sometimes we are more interested in the likelihood that a certain event will not occur. This is called the complement. The complement of an event A is the event not A. Complements add up to 1 or 100%. And there are several different symbols used to denote the complement of A, depending on where you look, which text you're using. So you may see A superscript C for A complement. You may see it called A prime. You may also see it as A with a bar over the top. I mostly use this first symbol, A superscript C for A complement, but there's no right or wrong way. Those are just the three most popular ways to write the complement of A. The probability that an event will not occur is calculated by doing 1 minus the probability that it will occur. Since they add up to 1, if you have a certain one of those probabilities, you can just do 1 minus it to find the other one. So in notation, what that looks like is that the probability of A complement is equal to 1 minus the probability of A. Another more advanced probability kind of topic or rule is the idea of intersections and unions, because a lot of times people have various attributes, or objects do, and we want to use the words and or to combine those into new, more complex events. So intersection is an and event. A new event that consists of outcomes in both A and B. The symbol for this is A, and then it's like an upside down U, B. That is the intersection symbol. And then there is the union, which is an OR event. This is a new event consisting of outcomes in A, or in B, or in both. The symbol for this is A, like an uppercase looking U and B. So I can remember that because this looks like a U. This is called the union. And a special note at this point is to notice that here, OR is what we call an inclusive OR. It also includes the AND. So that is a slightly different way that OR is defined in math or in stats than it is in maybe regular life and in English. So for instance, if I'm offering my son 2 pieces of candy and I say you may have the sucker or the M&Ms, I do not mean that he can have both. That's not what or usually means in kind of the real world. However, in math, if I were to say A or B, I also mean both. That's kind of included. That's why it's called the inclusive OR. So that's just something to be aware of. Mutually exclusive events are events that have no outcomes in common. It's impossible for them to both happen at once. So a special note here is that A and A complement are always mutually exclusive. Right? An event cannot happen and also not happen. That's not ever anything that makes any sense. So A and A complement are always mutually exclusive. Other events are also mutually exclusive. You just have to look at them and say, could these both happen at the same time or not? And this leads us to the addition rule for probability. So the probability that A happens or B happens, so the probability of that union, A or B, is calculated by taking the probability of A plus the probability of B, and here's the key, minus the probability of A intersect B. This you need to know, memorize it. It's very, very important. You have to subtract out that and, the intersection, the overlapped outcomes. Otherwise, you would count them twice. You would have counted them here. You would have counted them here. So because they were in both of them, So they got counted twice. So therefore you have to subtract one of those out. Otherwise you're double counting people or objects. In the event that you have mutually exclusive events, if A and B don't actually overlap, then this intersection part is 0. Okay, so if two events are mutually exclusive, we said they can't happen at the same time, so probability of them happening at the same time is 0. In that one case only, the probability of the union, the probability of the OR, is simply the two probabilities added together. Okay, but that's sort of that's because it's such a, honestly, it's like a more rare situation. A lot of events do have overlap. So in my opinion, it's safer to always use this original formula up here, because the worst case scenario is that halfway through it, you realize that you're subtracting 0 and nothing bad happens. You haven't even really wasted any time. You're just like, oh, okay. So I had this mutually exclusive case. Whereas the other way around is bad. If you use this and you forget to subtract out overlap that really is there, now your answer is wrong. So in my opinion, it's just always safest to start out with this formula and subtract 0, and nothing is harmed in that way. Okay, Venn diagrams. You've probably seen these in various places before, but what they do is they give you a visual representation of sets. The universal set U is the set of all elements of interest in a particular problem, and it's represented by the rectangle. And then the subsets are represented by circles lying inside of the rectangle. So we can use Venn diagrams to visualize all of these different ways that probabilities and sets can occur and overlap and things like that. So if you are looking at the intersection of two sets, visually where that is, or what that looks like, is it's where the two sets overlap. So any elements that would fall into this overlap area would be in the intersection. The union, remember, is anything in A, anything in B, and anything in both. So that would be all of the elements anywhere inside either of those circles. If we want to look at the complement as a Venn diagram or in a Venn diagram, remember the complement means basically everything that is not in whatever set we're looking at. So if I'm particularly looking at a complement, I'm saying not in A, so everything outside of the circle A. So any element that would fall in any of that shaded area would be considered in the complement of A. What about a Venn diagram showing A and B as mutually exclusive sets? So remember, again, mutually exclusive means there is no overlap. They cannot happen at the same time. So all of my images so far have sort of indicated or implied that they are not mutually exclusive. There's been this overlapping wedge in all of these cases that I would expect some elements to fall inside. So if I want to draw an image that shows mutually exclusive very clearly, what I would want to do is draw two circles that don't overlap, that show clearly that there's no way to be inside circle A and inside circle B at the same time. Another way, or another word that is sometimes used to describe this situation is disjoint. So if you have disjoint sets or disjoint circles, then that is also saying there's no overlap. So Venn diagrams can be very helpful when you're computing probabilities, especially if you are a visual learner or a more visual type person. So just take these as a tool that you can use if you need to kind of create some visual to help you to calculate some of these more complicated probabilities.